Okay, so I think this was the question. The question was a raised to power n b raised to power 2n plus 1. So there was another question we have done before, a raised to power n to b raised to power 2n. Okay, so I inadvertently told you that this is equal to a raised to power n b raised to power 2n plus 1, because if you look at this algorithm, if you look at this particular algorithm, what will happen that here the number of a's, whatever the number of a's will be, the number of b's will be double plus one. Okay, double plus one. Okay, so by by equaling these two push down automatas, what will happen, the language, the strings that are all not in the language is also accepted by this. Okay, so suppose previously I have built the automata something like this one. So if you think this was the previous answer, just let me see. Yeah, okay, so this was the previously attributed answer. So in this particular automata, if you're seeing the when the a's are 2, b's are 4. Okay, so if you look at this string will not be a part of this language. Okay, so this language is a raised to power n, b raised to power 2n plus 1. So when a's are 2, b's should be 5. So this is not a part of the language, but if I try to build the same automata for this, if I take this as equal, so it will be accepted, but it is not this is not a part of this language, but it is accepting in this particular order. So that is why I just want to correct my mistake in the previous tune that I have told you. So for this I have to build another, so that is not equal to this one. Okay, so I have to build another. Always try to check the strings. If the strings that are not supposed to get accepted in the language, if they are getting accepted, then your push down automata is not correct. Okay, so based on that, I cannot say that a raised to power n b raised to power 2n is equal to a raised to power n b raised to power 2n plus 1. So they are totally both different things. Okay, so how can you build a particular PDA regarding this? So it is very easy. So what will happen? You build the automata for this one, a raised to power n b raised to power 2n. Now, when you're seeing a single e, single b at the end, you just accept it. Okay, so it will most probably it will happen like that, z naught. Then there is a. If there is one a, there will be if there is, suppose this like this. Okay, so this is a raised to power n and b raised to power 2n. So a is 1, b 2 1 plus 1. Okay, so it will become a1 b3. Okay, so now what will happen when your pointer is here, you push two a's in the stack, and by seeing a 1b you pop it, by seeing a 1b you pop it, and then there is a 1b left. Okay, so when your pointer is at b, so the stack there will be a z node, so you just go to the final state. Okay, so you do nothing, so it will be b z node and z node, and you are going to the final state. Okay, so everything is same. So if I build the automata here, it will be suppose there is a when there is a at z node, you push two a's, it will become a z naught. When there is a at the top of the stack, there is also a, you will push two a's again, so it will become this. Now by seeing a b, you'll at the top of the stack there will be I, you start popping and you keep popping. When there is a b at the top of the stack, there is a, you keep popping until now your stack will be empty and your pointer will be, your input will be at b. So b, when there is a z node, when there is a z node, uh, you just don't do anything, you move to this state. If you want to make this as final state, you can do this, or if you want to make it by acceptance by the final state, you can also do this. Okay, so what you do, by seeing a b, you don't do anything. By seeing a b, you don't do anything, and what you do, the stack will remain as it is. Now the input is over, now the input is over. So it means that you are seeing nothing, and at the top of the stack there is a z node, so you do nothing and move to the final state. Okay, so that will be your push down automata, correct push down automata for this particular question. In the previous tute, I told it differently that these are equal, but actually they are not equal. Okay, so that was my mistake, and just see this to correct itself. Okay, So now the 12th is again based, we haven't done non-deterministic push down automata question. So that is why I've included this question. Now, if you're seeing, this question is somewhat similar to the question that we have seen in the tutorial one, only there is I equal to K and J equal to L here. So I just write the language here, I, J, K, L. Okay, so it is like this. So the first question is a raised to power I, b raised to power j, c raised to power k, and d raised to power n. Okay, so actually it is saying that a raised to power, I think, k. Okay, so just let me see the question. Yeah, it is e raised to power j, I raised to power, just let me, I raised to power k and j equal to 1. Okay, so okay, so I think I equal to k, and or there is a j that is equal to l. Okay, so already we have done it. So you can write this question like this one, that because I and k are equal, so you can write, suppose you can write it like this: a raised to power I, and then c raised to power I, because they are both equal, so you can write it here as it is. For b raised to power j, and I can write here as well. Okay, so I can write it here, but because there is a or here, so if you want to again write it more clearly, it can be written like this, that suppose this, first of all I will consider these two as equal. So it will be a raised to power I and c raised to power I do not considering this j, I will considering this as different. Okay, so d, l and l is different. Now I will take a union, and now I can consider this a, b and d as equal, b and d as equal, and a and c as different. Okay, so I can consider that I and k. So if you're seeing, this is again a or here in this particular thing, I is equal to k. In this particular thing, j is equal to l. Okay, so you can build a automata. So that automata is again a very simple here, there is nothing to it. So you can draw automata that can go here. Okay, so here you can build I equal to k, and here you can build j equal to l. Okay, so try this question. So first of all, try this question yourself. I will tell you the answer in like 2 minutes. Okay, try it first yourself. Okay.
Excuse me, sir.
Yes, yes.
Sir, in the assignment, you sent a mail yesterday. What do you mean you won't accept notes? So you want sir PPTs for the topic, sir?
No, no, handwritten notes means that you should prepare it in a proper formatted Word document. Okay, so you do not write the notes on the pen, copy and pen, and you just take a screenshot of that, and you put it in a PDF format. So that is the meaning of it.
So you want PPTs, sir, or can we use PP? Like for example, in video, I'll be using PPT. So can I use them as notes also?
You can use it as the PPT as not, but you have to prepare it in a Word file. Okay, so there is no problem in that, but it should not be in the form of PPT. Okay, so if you are preparing notes, I do not want any PPT. I want a proper notes. Okay, so if you okay, so that is why I've said that there is no need that the content presented in the video should be equal to the notes. Okay, so it can be different.
Okay, sir. So you want PDFs only, PDFs or Word files?
First of all, prepare a Word file and then convert it into a PDF. Okay, so how to do this question? It's a very simple one. So just let me clarify this. Okay, so this is a basic format that you can derive it like this one. So first of all, I just take this particular question, then I will start taking a union of this one. Okay, so I'm taking a raised to power I and c raised to power, where a raised to power I and c raised to power I. Okay, so it is like a raised to power I, c raised to power I, b raised to power j, and I think g raised to power, I think j equal to l. Okay, so these two are different in this particular one. So what I'll do, the first step is fairly simple, that you take a and then there is a no, you just start pushing the a. Okay, so all the a's are pushed onto the stack. So now what you do when there is a b, you don't do anything. So at the top of the stack there will be a. So just the a will remain as it is. You see a number of b's, you don't do anything. The a will again remain at the top of the stack. Now you will start to seeing a c, and c are equal to the number of a's. By seeing a e at the top of the stack there will be I, you start popping. Okay, so now what will happen when, because a and c are equal, so all the a's will be popped out of the stack, only z naught will remain at the top. So now when there is a z naught, then d will come. Okay, so now what you'll do when there is a d and at the top of the stack there is a z naught, you don't do anything. So just keep moving. Okay, so then there is a d at the top of the stack, there is a z naught, you don't do anything. Okay, so now in the end, what can happen, that you can go to the final state by accepting it. Okay, so it can be epsilon and then there is the z naught, and you can move on to the final state. Okay, so this was for this one, and then another one will be where b is equal to d. So it can be a raised to power I, b raised to power I think j, c raised to power, there is no, this is, I think this was k. So I don't think that these are equal, but these d and this was equal here. So this again I can write it as j. So I'll again build the automata for this only two. Okay, so in this one what you do, you don't do anything because a and c are not equal here, so there is no need to put it on the stack. You can see a, so when there is a and there is a z naught, you do nothing. Okay, so any number of a's can come. Now you are doing nothing. Now when there is a b, you start, you will push it onto the stack, so it will become b z naught, and then there is a b at the top of the stack, there is a b, you start pushing all the b's here. Now the c's are, again there is no need of c because we do not need to push it on the stack. So when you are seeing a c at the top of the stack, there will be I, you do nothing. Okay, so there will be a b at the top of the stack, you do nothing. So keep doing nothing when you're seeing c. And then when d comes, so because b and d are equal, so when there is a d at the top of the stack, there will always be a b, you start popping. Okay, so by doing this your stack will become empty, and at the top of the stack there will be a z naught. So your all the strings will be, I think all the strings will be empty. So z naught at the top of the stack, and okay, so there is nothing coming, so you can move on to the final state. Okay, so when there is nothing coming and at the top of the stack there is a z naught, so you do nothing, the z naught will be remain as it is, and you can move on to the final state. Okay, so now if you want to combine these two, because there is a union here, so how can you combine it? It can be combined because the first step is when the a is coming. Okay, so when the a is coming, it is pushing all the a's onto the stack. So what you can do, like this, that when the a is coming, so what I'll do, I'll do it like that. Okay, so just wait a second. When a is coming and at the top of stack there is a z naught, so I'll push a z naught. Okay, so that one. Now here when the a is coming, I will do nothing. Okay, so when the a is coming at the top of the stack there is z naught, so I'll do nothing. Okay, so now what you have to just remove some things, because at the q node I have already defined this thing. So when you have pushed a onto the stack, so this production is not needed, so that is why I'm deleting this production. And when because at the top of the stack now there is a, now another a come, it will be pushed onto the stack. Now here you see, here is a at the top of the stack, there is a z naught. So again there are a number of a's can come, so there is no need to remove anything. Okay, so at the final state also you can combine this final state into one state. Why define different final states? Okay, so you can define the final state as one, so it can be like this. So from this one, it can move to the final state like this. And from this one, it can again move to the final state like this. Okay. Okay. So that when there is a union, you can again first define this differently, and when there is a union, you can combine it very easily. Okay, so combination will take place in the first step. So always in the first step there is a also here, there is a also here. In this one you are pushing the number of a's, in this one you are not pushing the number of a's, you are just seeing the number of a's, and the stack will remain as it is. Okay, so that is the solution of this one. This again, this can be different, this can be different from what you have designed. If you have designed any different automata, just let me know. I will look onto that and tell you if there is any problem in that. Okay, so that is the solution in the similar way. See the next question again, it's also a non-deterministic push down automata, but in this one there is an and here. So for this particular question you cannot design a non-deterministic push down automata, because in the previous question, if you are seeing there, because of this or I am able to split the question. Okay, so this particular question will become I equal to I think it was I equal to k, and this was j equal to l. So that is why it is big, that is how it is becoming, because there is a or either the a will be equal to k, I is are equal to the number of c's, or the db's are equal to the number of d's. But if you're seeing in the stack, there will be at one particular instant there will be only one comparison, that the number of a's are equal to the number of c's, or the number of b's are equal to the number of d's. So there cannot be two comparison. I've already told you like this questions, that the number of a's are equal to the number of b's, that is possible. But you also, there is a third comparison, that the number of b's are equal to the number of c's. There is second comparison, but that cannot happen in a stack. So that is why you cannot build non-deterministic push down automata for this particular question, because there is an and here. But you can yes, yes.
Sir, generally for this kind of question, like it is not defined whether I is greater than 0 or greater than or equal to 0. Generally, what should we take, sir?
If it is not defined, you can take I and j is greater than equal to 0, greater than
Sir,
greater than 0. Okay, so it should be greater than equal to 1. Okay, so that if it is
okay.
not defined, automatically it is there, but in the question you can say that it is not defined, so it is not the correct one. Okay, so in all the questions it will be defined that I or j is greater than equal to 1. If it is not defined, so just that is a wrong question. So you can put that question in a doubt, because why I have been defined that I and j is equal to what. Okay, so in that particular you will always be given that what is the value of I and j. Okay. Okay, so now this is an interesting one. Now if you're seeing this is again a union here, and this one is different, it is a raised to power n, b raised to power n, and this one is totally different. The number of a's are double the number of b's are double the number of a's. Okay, so again take this one, draw it differently, take this one, draw it differently, and you can combine both of them, because there is a union operator here. Okay, so that is why this is a non-deterministic push down. Try this question, I will tell you solution in like 2-3 minutes. Okay, try it, it's very simple. Okay, so I'll tell you about the solution of this one, because there are these questions that I have to solve. So it will take a little bit of time for these three questions. So I'll do the solution of this one. So now this one is again fairly simple, because you have already done this question, as well as you have already done this question, because there is a or here. You can draw it differently and then combine it later. So there is no compulsion that you can use two different final state. If you want to use a single final state, that is also fine. Okay, so keep in mind that these two are again the same here, so they are again going to the same final state. There is no problem. Okay, so always try to avoid two different final state, because final state means that you have accepted, so it literally means the same thing. Okay, so and now I'll try to drive this one, a raised to power n, b raised to power n. So this is your first one and this is your second one, and then I put a union in. Okay, so the first step is very simple. You push the number of a's onto the stack. Okay, so now all the A's are pushed onto the stack. Now seeing the number of B's, you start at the top of the stack, there will be a, you start popping it. Okay, so just keep popping until you reach at the Z node. When you reach at the Z node, what you see, you just can move to the final state. Okay, so this will be your final state. For this one, for a number of A's, you can push two number of A's by seeing a single A at the Z node, and you can push two A's by seeing a at the top of there is a, you can push two a's again. Okay, so now by seeing a b, the step is again similar here. You can pop it, you just keep popping, and you can move to the final state by seeing epsilon and then z naught and z naught. Okay, so now there is a union. So if you're seeing here, what will be the first step here? First step will be that there is a and at the top of the stack there is a z node, and you are pushing a z node. So by doing this, there is no need, because the a is already pushed, so there is no need of this step. So I'm deleting it. In this particular one, when there is a at the top of the stack, there is a z node, you are pushing two a's in the stack. Okay, so now for this one, because the two a's are already pushed, so there is no need of this step. Okay, so now in the final one, you can, if you want to, you can again combine it here. You can do it like this. Okay, so take one final state and you can go towards this one and this one. Okay, so why this is a non-deterministic pushdown automata? Because non-deterministic pushdown automata will be different when you are the same input, when you are at the same input and at the top of the stack, and when there is a same input, I'll say same input and the same stack input, or what you say, same stack alphabet. Okay, so now check it, or no, though there is no or, there is a and here. Okay, so now check, there is a input a here, same stack alphabet z naught, same stack alphabet z naught. Okay, so now it is going, the q node is on the same input and same stack alphabet is going towards two different state, that is q1 and q2. So you can say that this is your non-deterministic pushdown automata. Okay, so that is why it is in non-deterministic one. Okay, so I think Chirag has also drawn the correct automata, that is the correct one. So I also draw the same, so that is, yeah, absolutely fine. Okay, so again, now the next question was on, it is on a Turing machine. Now this is specifically saying that the Turing machine is acting as an adder. Okay, so as an adder. So first of all, I just want to explain that what exactly this problem is. Now I will give you some time to solve it on your own, but it's a very easy problem. So what exactly means a adder? So you just have to add. Okay, so in this particular only use a unary input. Okay, so unary input means that only ones will be using, and I will separate. So this is your delimiter or separator. So I will say this is my a and this is my b, and I want to add of both of these input. Okay, so by adding, the answer, if you're seeing, this is your 111, this is exactly 3, this is your 111, this is suppose this is a 4. Okay, so in the unary, the answer here will be 7, but in the unary form it will be 111 1111. Okay, so it will be 7. Okay, so that now we are adding the numbers in the unary format. Okay, so the input that will be on the tape will be like this, 111. So I write it 1 1 1, and there is a separator. Separator is always denoted by a 0, and then there will be a 1. Suppose there is a 1 1, and then suppose there is a 4 ones. Okay, so now your pointer here will be blank blank, here will be blank blank. Now it's a very easy question, and your pointer will be at here. Okay, so now this is your A and this is your B. After adding it, I have to get this answer. Okay, so how? You just have to delete this 0 and place a 1 here. So what exactly you have to do? You have to delete this 0 and place a 1 here, and the final one will you have to turn it to a blank. Okay, so there are only two steps. First you have to delete this 0 as a 1, and you have to move to the final one. You have to move it to the final one, and turn it into a blank. Okay, so that now your tape will contain the answer. That will be your 1 2 3 4 5 6 7 ones. Okay, so this is a simple, very simple solution for this here. So again, there will be okay, so I'll tell you. So just try to solve this on your own. It's a very easy question. I will tell you the solution in like 5 minutes, but try it on your own. Okay, so how to solve this one? Okay, so I've already told you the step. Okay, and what you do, you just first step will be you, when you are seeing the one, you keep on moving right. Okay, so just what is happening here? Okay, so now the first step will be that your pointer will be at the one. So when you are seeing a one, you do not do anything, keep the one as it is and keep on moving right. Okay, so when you will occur, when you face a first zero, you face a first zero, turn it to one and keep it moving right. Okay, so now this step is already done here. Now now there will be again, there are a number of ones in that, there will be number of ones in that. So what you'll do, there will be number of ones, don't do anything, keep moving right. Okay, so keep moving right till you, okay, so this okay, so this was previously one here, keep moving right. Okay, until you get a blank. Okay, so when you get a blank, just stop. So it will be, when you get a blank, you don't do anything and you move one move to left. Okay, so now your pointer is standing here. Okay, so now when your pointer is here, change that one to blank. Okay, so it will be, when there is a one in there is at the pointer, there is a one, you change it to blank and keep moving left. Okay, so I'm moving left, because by turning it to blank, I am just taking the pointer to the starting. Okay, so that is the only there. Because it is just a courtesy to take your pointer at the starting condition. You can stop here, but that in all the books you will find this. Okay, so they're just the all the books, they have also defined that this is just a courtesy, that you move your pointer to the starting position. It is not a necessity. I'm that now I'm by making it B, I'm just moving my pointer to here. Okay, so now it is B now, so it will keep moving left when, because now all the things will be turned to ones. Now it will keep moving left. When there is a one, keep the one as it is and keep moving left until you get a blank at the extreme left hand side. Okay, so when you get a blank at the extreme left hand side, you just move towards one right. Okay, when there is a blank, keep the blank as it is and move towards the right. Okay, so now this will be your halting state. Okay, so keep in mind, because the Turing machine is acting, because the Turing machine is acting as an adder, the Turing machine is acting as an adder, there is no final state. Okay, so final state will always occur in acceptors. Okay, so final states are always in acceptors. When Turing machine is acting totally different, so it is now in this particular case, there is no acceptor, so it is not accepting the number of ones or the strings that is 0 1. It is not doing anything like that. It is just stopping at a particular thing by changing the input to something. Okay, so that is why there will be no final state when it is acting as an adder, it is acting as a transducer, when it is acting as a comparator. It will always, there will always be a final state when it is acting as an acceptor like finite automata and push down automata. Only then there will be a final state. Acceptor means that you give a string to a Turing machine, to give a string like 0011, it will say that yes, this string is present, or no, this string is not present. So that is your acceptor. Okay, so in this particular case, it is not acting as an acceptor. That is why there is no final state. Keep that thing in mind. It's a very important thing. Okay, so the next one as design a Turing machine which is acting as a copier. Okay, so copier means that it just copy the input. Suppose I gives you example. So again, I will explain the procedure informally. You just have to design the particular diagram here. Okay, will be that suppose there is input like blank. Okay, so now I have to copy this one in the tape. Okay, so preferably I will copy it to the right. You can also copy it to the left also. So it's your will. If you want to copy it to the left, you can copy it to the left, but I'm preferring it to the right. Now I want 1 1, so the output will be blank blank 1 1 1 1 blank blank. Okay, so that is what I want. So I have copied this 1 1 to the tape in the next towards the right of it. So how can you do this? I will again explain you the step. So suppose there are 3 1s here, and in here there are all blanks. Okay, so now what I'll first do, I'll first change the ones here. Okay, so I will change the ones when your pointer will be at here. I'm changing the ones to suppose something like x, x, now x. Okay, so now all the ones are changed into x. Okay, so now my next step will be that my pointer will be at here when I've changed the final one into x. Then I will move to the right of it when I occur a blank. Okay, so now what I'll do, the next step will be, suppose this blank blank blank. So the next step will be, this is your x, this is your x, this is your x, and this is my blank, and this is my blank, and this is my blank. My pointer is standing at here. Now I will convert this blank into a 1. So I will convert this blank into 1, and I move towards the right, towards the first x, and I change it to 1. Okay, again I will move it to the right until I find a blank and change it to 1. Again I move it to the left until I find a x and move it to the 1. Okay, so again this procedure will be repeated, and the ones will be copied. Okay, so try to build this one. The procedure is very simple, I already told you. So try to do this one on your own. Okay, I'll tell you the solution in like 5 minutes, but try it's a very easy question.
Sir,
Yes, yes.
sir, what do you so by added it, do you mean that we are appending the two numbers to together?
In the previous question.
Yes, sir.
Yes, yes.
Like you said, like seven ones are there. So did you just append these two strings together as an add for that? What did you mean that by adder?
Yeah, that exactly, that is the meaning of it, but I'm adding it in unary format, so that is why it looks like this. Okay, so this 0 is just a separator, and I just it's in place of this 0, I'm at changing it to 1, and the
Okay,
blank
sir.
and changing it.
So will the Turing machine work for binary additions?
Will the Turing machine works for binary addition? It can work for binary addition, but I have to get back to you on that. Okay, so I haven't seen
Okay, sir.
a particular machine, but my thinking is that it will be possible. Okay,
Okay, sir.
so try this question. It's a very easy one. All the steps are already explained. Try it yourself. Okay, so just let me provide you the solution. It's a little bit different than you expected because there is a certain kind of a loop in here. Okay, so loop is very simple. If you go step by step, it's a very simple solution. Okay, so I'll again go step by step. So first of all, I will convert all the ones to any symbol. So this symbol is X here. So in the first state, you will get when there are ones, change all the ones to X and keep moving right. Okay, so this is a loop, so it will again eventually got towards the blank here. Okay, so when there is a blank, you have to move towards the first left. Okay, so I'm not converting right now, so I'm you can go it like this: blank, convert this blank to 1, and then to this X to 1, and then again this and this. So I'm just I'm first converting this X to 1, but you can do it differently also, that you can convert this blank to 1. So that is the fine. Okay, so you can do it in both ways. So I'm just, when there is a blank, so I will be here. So when there is a blank, so keep the blank as it is, keep move to left. Now my pointer will be here. Now there will be a X here. Okay, so now what I'll do, because I do not want to create a loop here, I only want one. This is a one move, that this X will be converted to 1. So when seeing a X, now when I'm at the pointer is at here, when I'm seeing a X, I change it to 1 and I move towards the right. Okay, so when I see this one, I change it to 1 and I move towards the right, and towards the right, what will I get? I will get a blank. So now what I'll do, now this blank will be changed to 1. So now this blank, so what I'll do, I'll loop it here. Okay, so now this blank will change it to 1 and I move to left. Okay, so now this blank is now change it to 1 and I move towards left. Okay, so now by moving left here, now you are standing at Q1. So by moving left, there will be a number of ones. Okay, so there can be any number of ones here, and at that step there is only one, but there can be number of ones. So don't do anything on number of ones. Keep moving left. 1, keep the 1 as it is and keep moving left. Now you will find your X here and make the X as 1 and keep moving right. Okay, so now when you are standing at here, at when you are moving right, you will get the number of ones in between. Okay, so in the path, so what you will do, so when there is a 1, you keep the 1 as it is and keep moving right until you get a blank. Okay, so now when you get a blank, so make the blank as 1 and you move left. Okay, so I'll move left, and by moving left there will be a number of ones. You will keep until you find another X. Okay, so I'll find another X here. Now I'll change this X to 1 and I keep moving left. I move right. Okay, so now I'm in the path. I will get a number of ones. At the end I get a blank. Now I'll move the blank to 1, and then okay, so now I have to go to the final state also. Okay, so now there will be no X here. So when the final will be that you change the blank to 1. Okay, so now your pointer is at here. You change the final blank to 1. Now what you will do at that point, when uh, what can I do here? Blank. So because all the things will be changed to, okay, just wait a second. Okay. So now your pointer is at here. Now you will start moving. If you are at Q1, now you will not be able to find, there will be multiple ones here at the left, and you will find a blank. Okay, so because all the ones are over, now there is no X. So in that Q1 state, you will find one blank. Okay, so because you are keep moving left, you will find a blank here at the left, because blanks are infinite symbols on the tape. Now when you got a blank, don't do anything, keep the blank as it is, and you can move to left or to right, but I want to return to my pointer, so I will move a step towards the right, so my pointer will be there. Okay, so now this will be my halting state. Okay, so if you have any doubt, you can ask me. So I know that this is a bit confusing, But the final state, if you're seeing that in the final state, what will happen? So my pointer will be, I just explain you again. So it will be 1 1 1, and this will be your 1 1 and then blank. Okay, so when you are at this, the final blank will be converted towards the left. It will be converted to 1. Now all the ones are converted to 1. So now you are at here q1. Now when you are at here, you will keep moving left. You keep moving left until you find a 1. Okay, so this, because of this, I'll keep moving left, but I will not find a x here, so I cannot go to q2 state, but I'll find a blank. Okay, so when you find a blank, what you do, you can go to the halting state. Okay, so don't make this as a final state, because in this particular case my Turing machine is acting as an copier. Okay, so copier is again not a acceptor. Okay, so acceptor, when the Turing machine is acting as an acceptor, then there will be a final state, otherwise there is not a final state. Okay. Okay, anyone has any doubt, you can ask me here. I know it's a little bit different, but if you take a look at it, it's very easy. Okay. Okay. Okay, so this one, it's a lengthy question. I will take this question into the class. I don't think it will be completed in this tune. So that is why I will take this, the Turing machine, which is acting as a comparator. Okay, so comparator means that when A is greater than 1, A is greater than B, or A is less than B, or A is equal to B. Okay, so in digital, you know what exactly a comparator is. So I'll try to cover this in the class, in tomorrow's lecture. Okay, so the seventh question is again a very simple question. So it is again giving you a language. If you're seeing, this is a language, and you're just asked to identify a particular grammar from the language. Okay, so I think it's a very fairly simple question. Just take a look at this, but I think you can easily solve this. It's a very simple question, and tell me which is the option here, A, B, C, or D. Okay, so if you take a look at this grammar, it's a very easy one. Okay, so you can easily do it. Try it. Okay, so if you see this question, the first, so just ignore the LL here. So it's the compiler part. Just this is a left. This is just don't worry about this LL here. Okay, so just grammar for the language e raised to power n, b raised to power n, c. Now the c, the number of c's are equal to the combined number of a's and b's here. Okay, so first of all, in this language there is a lambda. You can see because n and m is greater than equal to 0. So there is a lambda. Okay, so just take a look at this. Which particular option cannot derive lambda here. So I think s tends to a s c, and then if you want to move further you can get to s1. So s1 can derive lambda. Again s tends to s1 can also derive the lambda. So lambda is there in the language. And understand this language what it is doing. The number of a's and c's are equal. What it is saying is the number of a's and c's are equal, and the number of b's and c's are equal. I think that is fine here. Okay, so just check the next option if there is a lambda here. So this lambda is again in the first step. Again a. Okay, so it is saying the number of a's and number of c's are equal, and the number of b's and number of c's. There is a problem in this one. Okay, so the functional problem is that when you got to s1. Okay, so when you got to x1 there is no stopping point there. Okay, so suppose s1 tends to asc. Now this s is tending towards s1. Now s1 is again b s1c. So now there is no how can you stop here. So what is the stopping point here? Because the it is fine that a and b's are equal to the number of c's, but you cannot stop here. Okay, so I don't think that will be the, you can directly see that this a b c c should be in the language, should be in the grammar, but it is not derivable here. Okay, so you can directly ignore this one and check. I think lambda is also derivable here. Okay, so the number of a's and number of c's are equal. Again there is a lambda, there is a lambda. I don't think there is a problem here. So just check it. Yes, c. And if I want to go further, s1 then b s1c. So number of is, I think that is fine. So just make this one and this one, just shortlist this one and move towards the d1 and d. Okay, so it is again deriving a lambda. There is no problem in that. Number of a's and number of c's are equal, but there is no but I cannot reach to s1. So again I can eliminate this one. I cannot derive this string a b c c. This string is not derivable from this one. Okay, so two are eliminated, only two are remaining. So see the difference between these two. The first one, the only difference between these two is there is a lambda in the starting one, and there is not a lambda in this one. Okay, so I don't think there is any problem if there is a lambda in them. Okay, so do both the grammar. Just let me see. Is there any string? Okay, so lambda can also be derivable from here. I think they are both equal grammars, but I think that was unambiguous grammar. This is ambiguous one. Just let me again confirm it, that there is only a possibility of a lambda here, but lambda can also be derivable from s tends to s1 and s1 tends to this one. By adding a lambda, is there any problem? You can get a AC here, but you cannot get a AC here. Just let me see. I think you get a AC here. You can also get a AC here. It will be ASC, and then S1 can be tends to S1, and then it can, so AC can also be derived. I think that both of the answers are right here. Okay, so just let me confirm it. Just wait for a second, but I think both of the answers are correct. If you are able to find anything otherwise, just let me know. Just wait for a second. Just 1 minute, okay? Just let me confirm it. Okay. So both are the correct answers here. Okay. So because if you're seeing that only the lambda, if you remember the equivalence property that I already told you, so only the lambda is here and not a lambda is here. Okay. So lambda can be also derivable from this language at S. So there is no problem in that. Okay. So if there is anything different, I will again let you know in the next tute. But I think it's the both answers are correct. Okay. So now only the one E and C are the answers here. Okay. So now take a look at the eighth question. So eighth question, if you remember the ambiguity one. So ambiguity is very easy to check. So if you are able to derive two different trees for the same input, you can say a particular grammar is ambiguous. Otherwise not. Okay. So see this one. You have to take the string yourself. Okay. So I cannot. I don't think I can help in that. So it will be. I'm just randomly taking it. So AB can be derivable from this A and this B. Okay. So I don't think that you can derive AB any other way. Can I? Okay. Okay. So I think AAB will. So let me see. AB, and then I want two A's here. Okay. So one A from here, and then I can go like B. So from this B, I can get this one. Okay, so it will be 1, 2, 3 A's and then B. Okay, so let me see if I can derive it from any other way. Aki, I don't think I can. Okay, so let me see. AAB. Okay, what can be other one? AAB. If AAB is possible, yes. Just let me see. S tends to AB. So this A becomes A, and then A, this B becomes A. So yeah, I think AAB can be a possible choice. Okay, so this one, this is a tree that is deriving AAB from here, and from this tree I can go S tends to AB, and okay, so I can go AAB. I want AAB, so there is no need. I can go directly AAB, and this B will be a B. Okay, so the string here is also same AAB, but the trees are totally different. Okay, so if you're seeing, so this G1 is completely ambiguous grammar. Now for this G2, if you remember what is ambiguous, that if you are able to derive the same string using different trees. Okay, so it is just ASBS. Okay, so I think that is also ambiguous. Can I just let me see? I think it's a little bit different than I anticipated. Okay, so now it is ASBS. Okay, so ASBS. So AB can be derivable from here, but I have to take a little bit far here. So this S can be BS, AS, and then this will be AB, AB. Can I get a BA? If I start with this one, well, okay, let me see AB. Okay, so AB. Okay, this one will be your this thing. It will be AB, AB, and this will be my S. Okay, AB, AB. I don't think AB, AB is possible. AB, AB. So if I take ASBS and put here, so it will be AB, AB. Yeah, I think it is possible. So just let me see. ASBS. So for this as I put epsilon here, and here I will put B as A. So this will be a lambda, this will be a lambda. Now this will become ABBA, but this is becoming ABBA. But I can do it like this. ASBS. ASBS. Okay, now see, this is ABAB. Now this is a totally different. So for this particular string, there are two different parse tree. So this grammar is also not ambiguous. This is all. Oh, sorry. This grammar is ambiguous, and this grammar is ambiguous. So ambiguous means when you are able to derive two different parse tree for the same tree. Okay. So I think I have taken your enough time. Okay. So only this ninth one is remaining. This is again taken from the same notes that I've already given you. You just try it yourself. All the questions are already done. So it is just for your these are the important ones. Okay. So again, I will confirm the seventh question. Again, I will confirm the seventh question, and I will tell you about the sixth question in the lecture. Okay. So and you can move on to the next lecture if you have any kind of doubt. You can ask.